Okay, today we're going to look at irrational numbers. Before we looked at rational numbers, now we're going to look at irrational numbers. And remember that we started off with the set of natural numbers. And the set of natural numbers was this set. 1, 2, 3, the numbers we used to count. Then we increased the set to the set of integers. And the integer numbers were these numbers, 0, and their opposites. So we had those numbers, 0, and the opposites of those counting numbers. So we had that set that we called the integers, and we were working with the integers. And then we moved on to the set of rational numbers. Remember the set of rational numbers. And in order to understand the set of rational numbers, you first had to understand the set of integers, which means you had to understand the set of natural numbers, because integers are just natural numbers, they're opposites and 0. So the rational numbers were the set of fractions such that the numerator and the denominator are integers, and the denominator q does not equal 0. So that was what we call the set of rational numbers. That was a set of rational numbers. Now, not every number can be written as a fraction where the numerator and denominator are integers. Any number that can be written as a fraction where the numerator and denominator are integers, any number that fits that description, when you write it as a decimal, it'll either be a terminating or a repeating decimal. So when you look at numbers in this set, every number in this set is a terminating, meaning it ends at some point, or repeating decimal. So now let's talk about the set of irrational numbers. Well, the set of irrational numbers is the set of real numbers minus the set of rational numbers. Well, a real number is just a number that doesn't involve the imaginary unit I. So if it doesn't involve the square root of -1, which is the imaginary unit I, then it is a real number. If you take away all the rational numbers from the set of real numbers, you'll get the set of irrational numbers. So the set of irrational numbers includes numbers like pi. Pi is an irrational number. The decimal representation of pi, if you write pi as a decimal, it never terminates and it never repeats. Well, it's not that it never repeats, but it doesn't have a sequence of repeating blocks. There's no sequence of repeating numbers. Pi, the square root of 2, is also an irrational number. Cannot be written as a quotient or a fraction where the numerator and denominator are integers. There's another number, e, which is used a lot in finance. That's also an irrational number. And there are many, many other irrational numbers, like the cube root of 7. There's many, many other irrational numbers. But the key to being able to recognize irrational numbers is that when you write an irrational number as a decimal, the decimal representation will never terminate, meaning there's no point where the number stops, and it doesn't have a repeating sequence or a repeating block of digits. So there's no way of putting a bar over any block of digits to say it repeats forever. So we started with natural numbers, we went to the integers. From there we built the rational numbers by making fractions out of integers. And now we're saying if you take all those numbers that are rational away from the set of real numbers, you get what is called the set of irrational numbers. Alright, so now let's try to identify irrational numbers. Okay, I also want to introduce you to another set of numbers called the perfect squares. The perfect squares are the squares of the natural numbers. So the first perfect square is the square of 1. The second perfect square is the square of 2. The third perfect square is the square of 3. The fourth perfect square would be the square of 4. Then the square of 5, and so forth. It continues forever. There's no largest perfect square. The smallest perfect square is the number 1, just like the smallest natural number is the number 1. but there is no largest perfect square like there is no largest natural number. So these numbers are called the perfect squares. Whenever you take the square root of one of these perfect squares, you will get a natural number as the answer. And every natural number can be written as a ratio of two integers. So whenever you take the square root of one of the perfect squares, you get a rational number for the answer. But if the number you're taking the square root of is not one of the numbers that is a perfect square, automatically you will get an irrational answer. So let's go ahead and do this. Here's an example. We are going to determine whether the number is a rational is rational or irrational. Okay, let's start with the number square root of 9. Well, the square root of 9 is 3. 3 is a rational number. Whenever you take the square root of one of these perfect squares, the answer that you get is a rational number. And it's a rational number, obviously, because you can write it as 3 over 1. 3 is an integer and 1 is an integer. So because of the fact that 3 can be written as 3 over 1, it's rational. All right. But all you have to worry about is the fact that the radicand, the thing underneath the radical here, the 9, is one of the numbers that we call a perfect square. Therefore, when you take its square root, you will get a rational number, or in this case, a natural number. Right, let's try the square root of 10. Oh, actually, I didn't make the determination. It says to determine whether this number is rational or irrational. This number is rational. And there's proof that it's rational. I just wrote it as a quotient or a division of two integers. Part B. So the answer is rational, but there's the proof that it's rational. The square root of 10. So part B, determine whether the square root of 10 is rational or irrational. Well, whenever you take the square root of one of the numbers that is a perfect square, the answer is rational. But if you're taking a square root and the number is not one of the numbers that would be in the set of perfect squares, then automatically we have that this is an irrational number. Now the proof of that is a little bit beyond the scope of the course of this class. So just take on my word that when you take the square root of one of the numbers that we don't call a perfect square, one of the numbers that's not the square of an integer, whenever you take the square root of a non-perfect square, the answer is irrational. Alright, so let's take a look at part C, square root of 25. Well, 25 is on the list. 25 is the square of 5. Therefore, this is rational. 25 is rational. Take a look at a D, the square root of 26. Well, 26, once again, is not a perfect square. Therefore, it's not the square of any natural number. Therefore, 26 is irrational. All right, let's try two more. Try the square root of 81 and the square root of 91. Well, the square root of 81, would 81 be the square of a natural number? Is 81 a perfect square? Why, yes. 9 is a natural number. 9 is one of the numbers we use to count, and if you square 9, you get 81. So 81 would be in the list of perfect squares. So 81, the square root of 81 then is a rational number. And the square root of 91, well, 91 is not a square of a natural number, so 91 is irrational. Alright, have a few more here actually. Those are the ones involving radicals. So let's take a look at example G. Let's try 1/3. Well, 1/3 is already written as a ratio of two integers. So automatically, because it's already written as a rational number, it is rational. Remember, a rational number is just a number that can be written as the division of two integers. Any fraction that where the numerator and the denominator are both integers is automatically a rational number. H. So let's see, H we'll do 0.424242, and then we have ellipses showing that this pattern continues forever. This pattern of repeating 4242, repeating 42, that pattern continues forever. So you can actually write this number as 0.42 repeating with a bar over it. That's what the ellipses mean. Well, it turns out that if a number is a repeating decimal, it's automatically a rational number. Just like 1/3. If you change 1/3 to a decimal, you actually get 0.3 repeating. Any repeating decimal comes from a rational number. So this decimal representation, the fact that it's a repeating decimal, means that this number up here is a rational number. So we have another rational number for H. Let's see. And let's do this last one, I. The number is 5.362. 5.362. Okay, well, this is a terminating decimal. This decimal stops right there. It's only tenths, hundredths, thousandths. So this ends on the thousandths place. And any terminating decimal is also a rational number. So there you have it. That's how you're going to determine whether a number is rational or irrational. All right, the other thing you're going to do is we're going to have to add, subtract, multiply, and divide these irrational numbers. So let's talk about, first, we're going to have to simplify them. So let's talk about simplifying rational numbers. The rule that we're going to use to simplify rational numbers is the product rule for radicals. It says that the square root of a product, the square root of a times b, is the product of their square roots, is the product of the square root of a and the square root of b. So this says that if you have a product underneath a radical, you can split it up into two radicals, with each factor being what the radicand for one of the radicals. Now, why is that beneficial? Let's see what happens, how we can use this to simplify a radical. Okay, now here's how we're going to do this. What we're going to do is we're going to look at our list of perfect squares. Remember, the perfect squares were the squares of the natural numbers. So 1 is a perfect square, 4 is a perfect square, 9 is a perfect square, 16 is a perfect square, 25, 36, 49, and so forth. Those are the perfect squares. So we're going to look at our list of perfect squares to find the largest number on this list that is a factor of 24. The largest number on this list that I can divide evenly into 24. Well, 16 is too large of a number to divide evenly into 24. 16 is more than half of 24. So 9 doesn't go into 24, but 4 does. 4 is a perfect square. 4 is a perfect square, but it's also a factor of 24. So this is what I'm going to do. I'm going to rewrite the number 24 as the square root of the perfect square factor I just found of 24. And what do you have to multiply by 4 to get 24? Well, that number is 6. So this equation is true. This equal sign rings true because 24 is 4 times 6. So the square root of 24 is the same as the square root of 4 times 6. Now we're going to appeal to this formula here, the product rule for radicals, which says that you can take a product underneath a radical and split it up into two radicals, and this is what you get. Well, the first thing is going to be the square root of 4, and the second thing is going to be the square root of 6. The square root of 4, I know what that is. 4 is a perfect square because it's the square of 2. Therefore, the square root of 4 is 2. And the answer, when you simplify the square root of 24, you get 2 square roots of 6. This will be the final answer for part A. Let's try another one. Part B. The square root of 50. So your goal is to find a perfect square, one of the numbers in that set, find a perfect square that goes evenly into 50, that you can divide 50 by and not get a remainder. Well, let me see. 25 is exactly half of 50. 25 is a factor of 50, and 25 is also a perfect square. So if you can find a factor that's a perfect square, then you can factor that number into the perfect square factor, which is 25 in this case, multiplied by whatever you need to get whatever is in the product with 25 to make 50. Well, 25 times what number gives me 50? That would be 25 times 2. So now I have a product instead of the number 50 underneath my radical. And this rule says if you have a product under your radical, you can split it up into 2 radicals. So I'll have the square root of 25 and also multiplied by the square root of 6. So here, we know that the square root of 25 is 5. And the square root of 6, well, that's the irrational part. So there you have it. Oops, where did I get 6 from? It should have been a 2, I'm sorry about that. So it's the square root of 25 times 2. And you break it up into the square root of 25 times the square root of 2. I was looking up here at this 6 for some reason. And that breaks down into 5 square roots of 2. So the square root of 50 is the same as 5 square roots of 2. That would be the final answer here. Alright, let's do another, part C. Part C, the square root of 54. Alright, now we need to find a perfect square that is a factor of 54. Let's see. Well, I know that in the number 54 there is a factor of 9. So let's take out the factor of 9. And if you multiply, what number do you have to multiply by 9 to get 54? That should be the other factor. So what is the number that I multiply by 9 to get 54? That number is 6. Now, I'm going to break this up into 2 radicals using this rule. It's going to be the square root of 9 multiplied by the square root of 6. And once again, the square root of 9 we know is the number 3. And we still have the square root of 6. So it turns out that the square root of 24 is 2 of the square roots of 6. But the number 50, square root of 54 is 3 of those square roots of 6. So if you just add an extra square root of 6 as a factor, you get the square root of 54. Alright, last one. The square root of 36. Well, this one is on the list. This one is a perfect square, so the answer will not involve a radical at all. The answer will just be a number that is called a rational number, and 6. So for parts A, B, and C, the answers that we got were irrational numbers. They still contain the radicals. But for part D, the answer is 6, which is a rational number. So that's how you're going to simplify. That's how you're going to simplify rational numbers. Alright, let me see. Simplification, and then there's multiplying, dividing, adding, subtracting. So we'll do multiplying, dividing, and adding, subtracting on the next video.